Alright, so this video is focused on the chapter on moments. We'll be doing some revision, so it'll be quite fast. I'll be going through certain main ideas in moments, and then we'll go through a few examples. Yeah, then that's about it. Alright, so first up, moments. Okay, so moments is defined as force, as a product of force, time and distance. Okay, so simply saying moment is the turning effect of a force, and moments can be calculated using this formula. Okay, so moment is a turning effect, so anything that turning effect of force, anything that is turned using the effect of force is called moments. So for example, I have a box, I rotate it such that it changes orientation. Right, these moments. I have a door, right, I open it so that the door looks like this. Okay, yeah, this is also moments. Okay, and of course there are many other examples. For example, maybe I push a ball up the stairs, right? Okay, so it needs to rotate. Yeah, okay, so these are all examples of moments. And of course the most classic one will be, I have a beam, a pivot in the middle. If I sit here, this thing goes up. This is also known as turning. Okay, so these are all turning effects of moment. Okay, but the force and distance here we are talking about is important. Okay, so let's elaborate on that. That will help us understand moment better. Okay, so first thing, okay, so what is the force we are looking at, and what is the distance that we're looking at. Now whenever we do moments, there are three things that we must know. Okay, the first one, extend the line of action infinitely. Okay, the second one, identify pivot, and the third one, connect pivot and the line that you drew in number one with a perpendicular line. Okay, so let me show it to you what I mean by these three rules. Okay, so maybe you want to take like 1 minute to write these three rules by the side, okay, so that you don't have to keep referring to these three rules. Yeah, and anyway, these three rules are something that you must be able to perform whenever you do a moments question, especially a more complicated one. Alright, so let's see. Let's start with a very simple question. Okay, so I have this, right? Okay, so let's say I have a box here and I have another box here. Okay, so let's say here, right? Now our first thing, let's denote this with blue, and let's denote this with another color. Alright, now so according to the first rule, extend the line of action of force infinitely. Alright, so ask yourself, where is the force for the blue one? So this is the force, right? This is weight. Extend it infinitely. Okay, so extend it with a dotted line, extend it infinitely. Okay, of course within the frame of the question, right? Okay, so if the exam paper gives you certain space, just extend it infinitely. Okay, the second rule, identify pivot. Okay, so where's the pivot? This is the pivot. Mark it with a cross. Okay, so mark with a cross. Okay, then third, connect pivot and the line that you drew in number one with a perpendicular line. Okay, so this is the issue most people have. Okay, so let me ask you, if let's say I have a point like this and a line, the perpendicular line is given by this, right? Okay, if I have this and this, the perpendicular line is given by a line like okay, so they are all perpendicular, and the red line shows perpendicularity. Okay, and I'm going to use a red line here to denote the perpendicular lines. Okay, so it'll be like this. See, this perpendicular. Okay, so now this is the distance that we are looking at. Let's call it d1. okay, and this is W1. All right, now we do the same for the green one. Okay, I know this is very simple. Okay, I know you don't have to extend the line infinitely for this question, but just make it a habit so that when other questions come out, okay, you'll be able to do it also. Alright, so same thing, I extended the line infinitely already. Okay, so let's call this W2. Let's call this W2. Alright, and the perpendicular line is here. Okay, so see this perpendicular. Okay, and let's call this D2. Okay, now in moments, right, we are concerned about this thing called the equilibrium. Okay, so when I place two objects like this and they are not moving, we can conclude that they are in the equilibrium. So if system is stable, not moving, okay, we can conclude that it is in equilibrium. Now there are two conditions for equilibrium. Okay, the first one being that net force equals to 0 Newton. Okay, that means upward force equal downward force. Okay, or rightward force equals to the leftward force. Alright, and of course there are forces in the other direction. Okay, and all opposite direction they must be equal. Okay, that's what I meant by when I say net force equals 0 Newton. Second one is that the net moment is 0. Okay, I think this is a good time to remind you of the SI unit for moments, which is Newton meter. Okay, so I'm going to write 0 Newton meter. Okay, this net moment equals 0 Newton meter follows this principle called the principle of moment. Okay, now principle of moment state that the sum of anti-clockwise moments equals to the sum of clockwise moments. In terms of presentation, in terms of working presentation, please do it like this. Okay, write this principle of moment, then you will write using principle of moments, sum of anti-clockwise moment equals to sum of clockwise moment. Okay, so you're gonna write this, you're gonna write this, and you're gonna follow this. Okay, now first, before you write W1 times D1 equal W2 times D2, okay, so maybe you want to write like this, equals to W2 times D2. Okay, so maybe you want to write like this. Now we need to verify if it's correct, because since you write clockwise, is this really clockwise? So we need to check. Okay, so let's do a check. How do I know whether it's clockwise or anti-clockwise? Now look at where the force is. Okay, so I'm looking at W2 now. Okay, since I'm using the green ink, right, so I'll look at W2 first. Okay, so following this arrow, okay, connect it to the pivot. Okay, so there's only one way to do that. Okay, and the direction of arrow remains the same. Okay, so connect it to pivot, the direction of arrow remains the same, so it's downwards, so you curl downwards and go upwards. Okay, you cannot go in the opposite direction because you are reversing the direction of the arrow. Okay, so we need to follow the direction of arrow. Now if you look at this is actually clockwise. Okay, so we are lucky that green is really clockwise. Okay, we'll do the same for the blue one. Okay, connect it to the pivot. Okay, following the direction is anti-clockwise. Okay, so this is how you do it. Okay, this is how you present your working. Okay, so it is okay. So this is it. Okay, but this is very simple. Okay, so let's go through slightly harder ones. Okay, there's this very famous question in your TYS that goes something like this. So I have a beam, right? Okay, and let's say it's being hung by two objects, so something like that. And over here, let's make it slightly simple, it's being hung by one object. Okay, so first thing first, there are like two system moments here, so let me draw it in yellow and red and then I'll erase it. Okay, so first is the big whole picture. This is one system moment. The second system moment is here. Can you see that? Okay, so let's give it some value, then we can try. Okay, so I think for like a beam following on by for like objects, I think everyone is good with that. You should be able to know. You should be able to know how to do this kind of question. Okay, where's the perpendicular distance? Or later we go through some examples that are not so direct when it comes to perpendicular distance. Okay, so first thing first, we need to identify all the forces. Alright, so the forces, let's label it as W1. Should I use different color? W2, W3. Now, please take note, okay? Like, if the question never mentioned anything about that this string here, or the pivot here is being centered at the middle of the uniform beam. Okay, so first thing first, this must be a uniform beam. Uniform beam means that the CG is at center. Alright, so if the question never mentioned about that, they will give you where's the weight. But if the question mentioned that it's a uniform beam, and you know that this is a 1 meter ruler, okay, so let's say this is 0.3 meter and this is 0.7, then you can safely assume that they have not given you the weight and you are supposed to label it yourself. Okay, so first thing first, let's look at this. Okay, I think this is quite straightforward. So let's say we call this D1 and we call this D2. Okay, sorry, should be split, right? And we call it D2. Okay, so basically we have over here for this system, we have W1 D1 equals to W2 D2. Okay, so that's for the blue color system. Okay, now the next question, right, will ask like, what is the moments for this entire system? Okay, and that's where the interesting part comes in. Okay, so first thing first, identify where's the pivot. So the pivot is here. Alright, then we need to do this. You may want to redraw the diagram, okay, and then it becomes very straightforward once you redraw the diagram. So the diagram, right, because this thing is in equilibrium, okay, so you don't have to be concerned with it. Alright, so now you can redraw the diagram, and the diagram will actually look something like this. So let me redraw it nicer. Okay, the diagram will actually look something like this. This is 0.3, this is 0.7, right? Then you have your W4 here, your W3 is here, and you have one more. It's over here, and it's called W1 plus W2. If you want to group it and just call it W5 altogether, okay, then that will make this expression much simpler. Okay, when we do the expansion. Okay, so first we identify is it a clockwise or anti-clockwise moment for each of them. Okay, so using the method I taught you all. So first thing, this is the pivot, right? So connect it, draw the arrow, this is anti-clockwise. Connect it, draw the arrow, this clockwise. Connect it, draw the arrow, this clockwise also. Okay, so using a principle of moment, right, we can actually find out the answer already. Okay, so using POM, sum of anti-clockwise moment equals to sum of clockwise moment. Okay, please don't write shortcut like this during exam. I'm just using in this video. Okay, so we have W5, okay, times 0.3 equals to the red one first. So W3 times 0.7 plus W4 times 0.2. Okay, because the center of gravity, the weight of the beam, will always be at the 0.5 mark. So if that is the case, right, then this is 0.2. Okay, so this will be your answer. And go and look up in your TYS for under the chapter of moment. This question should be there. Okay, so if you are not sure, go and look at it. Okay, the last part that I want to go through, right, is when the perpendicular distance is not so obvious. Okay, so let's say I have a box. So I have a ground and I have a box here. Okay, so I want to shift the box, right? So I shift it here. Okay, the first thing is I exert a force here, F. Okay, this is a uniform box. In other words, right, there's a weight. So the weight, sorry. So the weight is here, okay, at the center of the box. Okay, so it's at the center of the box. What we're going to do here is we're going to use the methods that I taught you all, these three methods, to do this question. Okay, basically the question is find F in terms of W, okay, given that the sides are L. Okay, so that's the first question. Find F in terms W given the sides, given that the sides of the cube is let's say 2 meters. Alright, okay, or let's call it L meters. Alright, so L meters. Alright, so in terms of W and L. Alright, so the sides are all L. Okay, this is a square. Okay, so maybe you can pause the video here and try the question on your own. Okay, but if yeah, of course, obviously I'll be going through the answer. Okay, so I'll go through the answer from here. Okay, now it's suggested that you try it on your own. Okay, so first step, extend the line of action of force infinitely. Okay, so this is the force, this is the line of action of force. Okay, line of action of force just shows you where's the direction of force is acting in. Okay, so this is the line of action of force. You extend it infinitely with the dotted line. Okay, as long as you don't go out of the paper. Okay, second, identify where's the pivot. Okay, so in this case, this is the pivot. Okay, because you're going to rotate the box in this manner, right? And this will be the point where it will not move at all. Okay, so this is the pivot. Okay, so if this is the pivot and this is the line of action of force. Okay, so very simple. The question is, if I line like this and I have a pivot here, where is the perpendicular line? So you will tell me that it is here. Okay, so it is there, and let's draw it in. Okay, so this is the perpendicular distance we are looking at. So the perpendicular distance for the green force is, or rather for the green force. Okay, let's change the green. It's L. Okay, how about for the blue one? Okay, so this is the line of action of force. Extend it infinitely. Identify where's the pivot. Draw a perpendicular line from the line of action of force to the pivot. Okay, now this is L over 2. Okay, so next, the last thing that we need to do is to identify, is it clockwise or anti-clockwise. Okay, so same thing, connect to the pivot, and then you realize that this is anti-clockwise. Okay, next, connect this to the pivot, and then you realize that this is clockwise. Okay, so I'm just going to write here using principle of moment. So same thing, sum of anti-clockwise moment equals to the sum of clockwise moments. Okay, so anti-clockwise moment is in blue. Okay, so we have W times L over 2 equals to W times F times L. Okay, so next use the just manipulation, then we'll get F equals to W over 2. Okay, and this is how I give them the answer, right? Find F in terms of W and L. In fact, there's no L, so F equals to W over 2. So in this case, we need half of the weight to push, half of the box weight to push the box, to rotate the box one round, to rotate the box 90 degrees. Alright, and so this is the slightly more complicated one. I'll start the video here. I hope this helps. Okay.